Okay. Assalamu alaikum. Uh, Today, inshallah, we will have another talk or another lecture. Inshallah, we will talk about physical characterization of heterogeneous catalysis. Actually, as I just mentioned, it is the most important part in your work because it gives you a chance to know what is the material you are treating with, and if you are going well and already prepared the desired material or not, and the material which is in your reaction is the same as you want and uh, make the suitable or the expected or the desired mechanism or not. Okay, let's start to not waste our time. This is a physical characterization. Of course, you know that several techniques are used in this purpose, which is the characterization of heterogeneous catalysis. Not only heterogeneous catalysis, but characterization of materials, because these tools also are used for characterization of other materials in geography or in geology or materials in medicine or something like this. Not only heterogeneous catalysis. The same tools are used there as well. Okay. What is the main principle of these tools? All of it, of course, they are divided into several basics like thermal techniques, like for example BET or TBD and TBO and TBS and so on. This is thermal techniques, or DTA, TGA. These are thermal techniques. It depends on heating the material, and maybe spectroscopic techniques like X-ray, IR, XPS, and so on. Every or UV, every tool depends on your effect on these materials with an effect like temperature or like light, whatever the light is. It may be infrared, it may be UV, it may be X-ray, it may be something. And you detect what is the effect of your effect on these materials. Okay? That means you detect the feedback of your effect on these materials. Several spectroscopic, microscopic, these are this is radiation of a catalyst with X-ray, for example. Photons generates and photoelectrons which are employed in X-ray and XPS and something. This means that you detect the effect if you feel if you find this is catalyst, and you may affect on this catalyst with several effects. After that, you detect the effect or detect the feedback from these effects. Let's have, of course, I'd like to remind you about these effects may change in time, change in scale of the material size, change in scale of how much heat you need to do, a change in scale of how much pressure you need to do. For example, some in pressure, some techniques needs vacuum, meets high ultra vacuum medium. This means nothing at all on the sample. Okay, on your sample. Others need or don't mind if there is real conditions there, like this sample is in air or has some absorption on this, and so on. And others may need very high temperature, and like TBD, or as I just mentioned, those tools depend on the temperature, like TBD or DTA and something. And others need may detect the material in very small particle size in nanometer scale, 1 nanometer, 3 nanometers, and this scale. And others may detect the material or can check the material in large particle size in micrometer scale. These are, you may use ultra high vacuum or very high pressure, or some methods use in liquid nitrogen temperature, which is very low temperature, and the others use very high temperature. And some methods use like in you detect, you try to detect the conditions and the material in the real conditions. Like if you want to make an experiment for the purification of water, so you have to go to some place which has wastewater, like in the cereal field. So you bring real, which is waste real water to make your experiment. This is the real thing. But if you want to imitate, you can just check the degradation of dyes in water or something. This is not the real thing. Just imitating the real conditions. We have some methods. I will try to explain some of these methods which are used in the characterization. We have traditional methods, like there are two types of absorption. Of course, we just checked yesterday, and we will depend on this physical absorption or chemical absorption in some of our, not our, in some of the used techniques in characterization. Let's see how it will be. Number one, only I'd like to remind you about this. Number one is that determining the surface area and the surface texture. This is one of the traditional techniques used for the characterization of the catalyst. This is very important to know how much is the surface area of the catalyst and what are the surface properties that you have, like surface area or external surface area, internal surface area, micropores volume, or even the aperture or the opening of the pores, how much it is, because it will be benefit for you or beneficial for you to know the what kind of material for selectivity it can be used, as we will mention later on, inshallah. This technique you can measure surface area, the volume of by detecting the volume. If you remember yesterday, we mentioned about monolayer volume of gas, which covers all the surface. If you measure this, you can easily measure the surface area of your material. I think we explained yesterday. Okay. This technique measures the monolayer volume, and also this is, of course, this is chemical absorption, and also it makes a kind of physical absorption to measure other parameters, like, as I mentioned, pore volume, mixed condensation, and so on, mixed condensation in the pores, and so on. It makes isotherm. Of course, I'd like to remind you about what's isotherm. Isotherm is you measure something at constant temperature. You measure something at constant temperature. So you measure absorption at constant temperature. Okay, that's what will we will be explained just now. This is the old technique, not old technique. This is the old system that we were used. I myself used something like this. This is the old system that was used for the detection or measurement of surface area. If you can see, I will not explain the system, but only the part of the sample. This part of the sample has two cells. Okay, one is a reference, and the other one is containing one our sample. Okay, and we heat it by a heater. Just add a heater in the same like the same way. We add a heater and heat it to evacuate the surface. After evacuation of the surface, after it's being clean, now no gas at all, we add our gas, which is nitrogen adsorption. Make nitrogen adsorption. After adding the nitrogen, we just take how much nitrogen is absorbed, and then we plot the absorption curve. After that, we make evacuation and measure how much gas is evacuated and make a desorption curve. From absorption and desorption curve and its shape, we determine the exact shape of the, but with, of course, with some calculations, not only with the shape. Some calculations, we determine all the texture parameters. And this is the, okay, this is the new, this is the new, this is a new technique or new instrument that is used for the that's used for BET. And of course, this is not the only one. There are several shapes of this instrument, several shapes, because each instrument you will see in your life will, its shape will depend on the company which will produce this instrument. Okay, let's skip this. Of course, these are other shapes, and this is what we are talking about. These are the absorption isotherms. These are the only, it was 5, and they recently added a 6th one. This is the only 6 shapes for absorption isotherm, as absorption isotherm. The first one, second one, third, fourth, fifth, each one of these makes indicate a character or the properties of the surface. Let's check one by one. Type 1 isotherm, of course, this indicates a Langmuir adsorption. Langmuir adsorption, because it is talking about only monolayer adsorption. Monolayer adsorption. So monolayer, of course, directly your mind should go to chemical absorption and Langmuir isotherm. This point, this black point there, indicates that saturation of monolayer has gone, is obtained. This is type 2. After saturation of monolayer, the volume, absorbed volume, the y-axis is the absorbed volume. X-axis is the pressure, is the applied pressure. Increasing this curve means the absorption increases, the amount absorbed increases. This means if the amount the amount absorbed of nitrogen increases after monolayer, this means we still have chemical absorption, or we change it to physical absorption. Condensation of the gas will happen, and the absorbed amount will increase like this. Of course, there are other shapes like this shape, type 3 and the type 5. Both are physical absorption. And type type 5 is like this. Of course, it combines physical absorption and some parabola up there. This is type 4 is different, and this is the most important part in catalysis, because most of the catalysts which have pores have this type of isotherm. This is an example of the data you can obtain from. This is our data in one publication. As you can see here, you can find the first column on the left. These are the samples we used. The second column explains how much is the total surface area you have. The second one is the theoretical surface area. The Next one is microporous volume or surface area. The other one is mesoporous because you can measure microporous volume and mesoporous, and the external, this is external surface area. So if you subtract external from internal, you will find that internal surface area is very huge. Pore volume, the pore volume, and if it is micropore and or mesoporous material. And what is R? R is the radius of the opening of cavity or channel, and this is C constant. It is very important to determine the nature of your material. And this is microporosity. How much is it? All of this data you can determine from these isotherms. After some calculations, there is another T plot you can also obtain from these isotherms. I think we just gave you a general idea about surface area measurements and what you can get and what you can do with this technique. The other technique, which is also a very important technique, that you will use to see and detect what is the surface composition of your material. If it has acidic sites or basic sites, or even if these basic or acidic sites are strong or weak, and what is the type of linkage between these sites, you will see here. This is TB. TB means temperature programmed techniques. Temperature programmed techniques, you can, this is an expression. You can add a third word to this expression according to the technique you will use. It may be, of course, this is a technique measures the reactivity of a solid as a function of the temperature under controlled conditions, of course, and the temperature at which species react on the surface or indeed are desorbed from it, because the temperature of adsorption or desorption determines how strong your site is, if it is a strong acidic site or strong basic or weak, or because the temperature, if it is high temperature of desorption, for example, this means it's strong acidic site or basic site, and vice versa. Of course, we have different techniques from this TB, which are as I mentioned. But if you change the absorption, you will have different data from each and have more information. The more reactive species react at lower temperature, and vice versa. Of course, it is more reactive species react at lower temperature. But if this is if you make adsorption, and vice versa, if you make desorption, then the more reactive species will desorb it at higher temperature. The most common TB techniques are temperature programmed desorption, temperature programmed reduction, temperature programmed sulfiding, or temperature programmed oxidation. Those are the most important ones, and I think you can find the others. Of course, it is depend on the functional group and the absorption. Let me show you something. Also, it is realistic. It means that you add some adsorbent or some gases on the surface, and it measures the effect of desorption. This at the presence of gases, it is realistic. Yes, you can monitor the changes that the catalyst precursor goes through during the calcination and activation steps. Let's say check something here. In sorry, this is repeated again. This is the technique of temperature program. I think you can see here that this sample, in this sample, I will not explain all of this because these are just valves and reservoirs of gases and a sample holder. This sample holder, we just make heating and uh, uh, to evacuate the sample and make it very clean from all gases, and then add I'm sure you know nitrogen, liquid nitrogen trap, and not liquid nitrogen. It's a reservoir of liquid nitrogen just added here to make absorption at very low temperature. Then evacuate and measure the output of the gases. In this case, this depends on GC very much, because how come it depends on GC? Because it measures the amount or the intensity of the gas that enters to the sample, and measures the conductivity or the amount of the gas after going out of the sample, and it measures how much the sample took from this in this case. This is a very simple. No, this is modern one for this characterization, and in this case, it has many of the types of TBD, TBR, TBO analyzer. It has all. Just you click and you can make it as you want according to the gas you add to this instrument. Uh, this is a simple diagram, shows how it works. Of course, reactant gas you input in this the gray cylinder is the reactor, or it's the place of the heater. It's around it, okay? And this is catalyst sample. The gas goes to the catalyst sample, make absorption. After and of course we control the temperature at this time, and then thermal. You measure the gas after going out from the sample like this by mass spectrometer or by any technique, or by GC. This is and this is the data you can get it from like this. These are three samples. The first one is copper oxide. The second one is cerium oxide. The third one is a mixture of copper oxide and cerium oxide. I think you can easily distinguish the difference between the three samples. The first one is copper oxide, has a peak around 200 degrees C, but adding cerium, it shifts this peak to lower. That means that it made the acidic side is or basic side is little bit weaker one. After that, there is a difference in higher range of temperature as well. You can check here the effect. Also, I have something to tell you, that you don't invent science. I mean, you always depend on previous people data. I mean, you before going uh, to any experiment, you have to check what the other people did before you go to this experiment. I mean, this is literature review about what you want to do. Just check what the other people did before you, and what they already said, to just to continue after their knowledge, to build your knowledge on their knowledge. That means which they say that before 200 it means something, and after 200 or after 600 it means other thing. You are taking this information from your in your consideration, and build on this. Another advice you have to take it: don't take anybody's data as trusted data. Okay? No, sorry. Don't take any data from any literature. I mean, you just rely on trusted data. Also, I want to say that you don't rely on the other people interpretation, which is because I can see this data. I have a point of view or understanding or realizing or understanding this data. It's my point of view. It's according to my understanding and what I get and what I add new data, and so I explain this data. You may explain this if you see this data, and you may explain it better than me. You may have a better knowledge or better understanding for this data than me, even if it's my data. If it's my data, yes, but uh, anyone can understand it better than me. Somebody may understand it better than me. Okay, so don't rely totally or completely or on what I said. Criticize what I said sometimes. That's why some schools make a kind of review seminars, not regular seminars. They say it review seminars means I try to find a topic and search the previous literatures about this topic, maybe 10 articles. I add these articles and criticize, not criticize, understand the data without what the people or those people said about their data. For example, this is a type of our data. I will show you. Uh, of course, this is what I already mentioned about the data. These are my data, okay? But you may understand it better than me if you read and try to understand it. This what I did here. I added carbon monoxide plus oxygen in equal ratio to make simply to make CO2 as a product. Okay. Of course, people are trying to oxidize CO because CO is much harmful than CO2. On two samples which are platinum on Y zeolite and the platinum iron on Y zeolite as a mixture of metals. I just added CO plus O2. At this time, I got peak at 141, maybe 140 for platinum iron. In the same time, only one peak for platinum Y was obtained very high, over 440, 50. Sorry. So I checked the literature. I found that they classified or make it three zones. The first one is low viscosity sites where CO2 was dissolved below 150. This is CO2. Okay. If it's CO, it will be in another region in another place. And this is medium sites which around 400, and high or very high viscosity sites which are above 400. This means that this site or this surface has basic sites. We of course we didn't expect it, but it is basic. They are basic sites. Of course, we have other things we can mention here, but of course, I want to go to a very important technique that maybe you will daily use. This technique is like TBD or surface area, you may not use it so frequently, but for XRD, you will daily use it. Why will you use it daily, not Delhi? Daily, because it shows you or it informs you about the structure of the material you have. It gives you several informations. The first one is basically if your material is amorphous or crystalline. The second purpose is what if it's crystalline. If it's amorphous, of course, you will full stop and leave this technique. That's it. If it's crystalline, you go to next step. What is the crystal structure of your material? This is the second point. Where shall I get it? Will I just look at it and find the crystal structure? No. There are some cards. Previous people or very high or trusted organizations has some cards. It shows you this peak for this material, which has, for example, copper oxide. It has copper and oxygen. The material which has copper oxide may be number one, copper 2O. Sorry, copper 2, yes, copper 2O. Or copper O, or something. This means that if it's Cu2O, this means it will give you peaks somewhere. And these peaks will have some characters, something. And if it is copper O, it will give you other peaks somewhere, and so on. Okay, let's check. So number one, if it's crystalline or not. Number two, what is the structure of this crystal? Number three, what are the d spaces or let's parameters of this material? Number four, what are the crystallinity? And number five, it may give you the crystalline size by something or some equation which is called Scherer equation. It gives you crystalline size. Let me check with you. This is an old version of X-ray, and this is a new version of X-ray, and this is newer version of X-ray, which it has also bench top X-ray in this size or this size. Bench top means you can just move it from here and there. The others, it is only will be fixed in a room, an entire room. And this is very small, and the geologists are using because they can move it. And before going to spectra, this is a spectrum of radio waves, microwaves, infrared, visible, ultraviolet, X-ray. Of course, these two X-ray is one of the highest frequency or lower wavelengths techniques. So it is very dangerous. Basically, it is like this. Of course, this is the main idea. On the left hand, this is X-ray tube. This is the source of X-ray, and in the middle, this is the sample, and on the right there is a detector. That's it. Rotation occurs to change the angle of incidence, and this detector will record the data given. Of course, I'll not go deep in this technique, but I mean in this point, but we will understand more about it. This is the X-ray, and of course, these are the reasons why we use X-ray. And this is Bragg equation. This is whenever you study X-ray, you will find this equation. Whenever you want to know something about X-ray, you have to go to this equation. This is D. In this equation, it can determine the D value. D, which is D spacing, is the distance between two lattice planes. Of course, I'll show you what are the distance of lattice planes. This is the distance of lattice planes. This is the layer, first layer. Of course, this is what we just mentioned in previous studies. This is a source. It goes to the sample, and of course, rotation. This rotates from here and like this, like this, like this, and this is reflected to the detector here. These are planes. This is the first plane, second plane, and so on. Of course, this is incidence or X-ray. This goes to the first plane, and this goes to the second plane, and they are reflected here and detected here. Okay. D spacing, this one, this area, this distance is the D spacing. We can determine this value, this D spacing, from the difference from these passes. Okay. Of course, here, this is a lower one, is the chart we can get. This is a silica sample. This is the lower one. The lower one is a kind of the crystalline silica. When it has crystals or crystalline form, it will be like this. Not only like this, but this is one of them. And if it's amorphous, it will be like the upper one. This is amorphous sample. Now we will go to first slide. We determine the D value or crystalline structure, and this is Scherer equation. Scherer equation, it determines the crystallite size. Crystallite size means the crystal after forming the crystal. What are the size of this crystal? Of course, I will show you how can we. D is the D value. Of course, it is from the table. And K is a constant. This is dimensionless. It is 0.89. It's according to the using when you use copper, it is like this. And the lambda is the wavelength. Beta is full width of half maximum of the diffraction peak, and the theta is the Bragg angle. Theta is the Bragg angle. I'll only explain what's beta in this figure. Beta, if you consider this is a peak, okay? You measure the height of the peak and divide this height into two. Of course, mostly you will not need to do this because mostly the new instruments can calculate it easily without your uh, without your uh, without your work. But new instruments calculate it, but only I'll just give you what is its idea. The height, you measure the height because you may need it someday. You measure the height, divide this height by 2 to go to the half width, and measure this half width and transform it into radian values. And then you can apply in this equation and determine the D, which is not particle, crystalline size. Now I think we just introduced a simple idea about XRD. Now we will go to another technique which depends on light as well. No, which depends on another thing, which is electrons. This is electron microscope. Actually, I just told you that XRD is the most important technique that you will use daily in your work. TEM may be the same or next one. Why? Because it's your eye, which you will see what did you prepare. It's your eye, because it's like that if my naked eyes is looking to this guy, and I see he has glasses, he has nice shirts, he has nice eyes, he has nice hair, he has. I'm not flirting with you, don't worry. Okay, I can see him clearly. This first. In electron microscope, of course, if you want to see very small insect or very small organisms or very small thing, I can't see it with my naked eye. I have to use microscope, optical microscope. Optical microscope. Uh, this is optical microscope, okay? You can use optical microscope. It shows you some micrometers, okay? And if you want to go deeper to like DNA, to check DNA or to check something in atomic scale or nanometer, you can't use this. Or this one is SIM. It can't go to nanometer scale, but it will go to micrometer scale and you can see it. And this is TIM. Of course, it's huge. because it has many sophisticated equipments and parts. But let's go to previous slide. Uh, of course, electron microscope. It's like electron microscope is like optical microscope, but it uses electrons instead of light. It may be transmission electron microscope or scanning electron microscope. And I just showed you the picture of these three devices. And let's compare between optical microscope and electron microscope. The optical microscope uses visible light, but electron microscope uses electron beam. With resolution, electron microscope light lambda is used around maybe the wavelength is 200 nanometer. Where in electron microscope it goes to 0.1 nanometer. The magnification in optical microscope it may be 1,000 or 2,000 times, whereas in electron microscope it may go to 1 million times or more. Sample preparation in optical microscope is very easy and very simple, but in electron microscope it's little bit sophisticated, and I'll show you how. For cost, optical microscope anybody can use it. Like anyone can buy it. You can find it here in this university. I'm sure you will find many in this university. Okay, but in electron microscope, if you find one or two, it will be very enough because it's costly. Okay. For accessibility, anyone, as I mentioned, anyone can use it. In electron microscope, technicians, professional technicians, who will use it? Nobody else can use it. I can't use it by myself. I have to ask a technician who is well trained to use it and make some samples for me in my presence. And this is another advice I want to tell you. Sometimes some people like me may give samples to somebody. Please make this as for TIM or for SIM, especially for TIM or for SIM. Okay, and you just take it. After some time, he will send me data through email. That's all. This is not good at all because you prepared these samples. You are the manufacturer of these samples. You know what you are looking for in these samples. So please, what will you do is you go to the instrument by yourself, sit with the technician just beside him, and look at your sample. Oh, I need this picture. I need this picture. No, neglect this one. This is not good one. No, resolution is not good. Oh, please focus on this. It's astonishing or it's surprised to have this particle here. Please have it. You understand what you prepared and you know what did you prepare. So please do it by yourself, in your presence, not by yourself, because he will use his machine, but you will use your eyes to check what you want. Okay. Another, this is the types. Of course, there is sometimes like compound stereo fluorescence. It's not our topic, but in here in electron microscope, it is TIM or SIM. Let's go to how it works. For SIM, for example, I will not go in deep in these techniques because even I can't, I don't understand all about it. Just I know what I need about it. Okay. In these techniques, in SIM, electron goes from the source to lenses which are just make it narrow and condense these electrons and accelerate these electrons through these lenses, and the detector to know what the exact beam has, and then the sample, which is the pink one. Reflection of some electrons will occur, and then detector will detect these samples and show me the picture on the screen. This is it. Okay. In case of scanning electron microscope, some of the beams electrons strike. Okay, It just says what I have just said. In TEM, transmission electron microscope, the story is different, little bit different. How? Because this, of course, they have the same electron source and the lenses to filter and condense these electron beams, and goes to the sample. After that, some electrons will pass the sample and lenses, and I'll try to see what the sample left, or what are the beams transmitted from the sample, like this. An electron beam hits the sample, and the transmitted electrons are magnified again, because I can't see in this stage. It will be magnified again and again and again until I can detect it and see it. Okay, like this. Of course, this is. Of course, I want to say that we just mentioned that in SIM or TIM may go to more than million times. TIM and SIM may go to more for magnification more than million times. And for TIM, it has two types. The first one is older one, which is only TIM, TEM, and the newer one, or the highest resolution one, which is HRTIM, which high resolution TIM. Okay, a high resolution TIM magnify to the atomic scale. We will see. Oh, this, what is this? What is this? This is the sample holder. This piece of copper. It is seen. It is only maybe half centimeter diameter. This one, half centimeter diameter. This piece of copper, it's called grid. This is the sample holder. You just prepare your sample. I'll tell you how to prepare your sample. Just take a piece of sample, a piece of this sample, and to put it in a solvent. This solvent will not solve this sample, of course. It will it will be a kind of suspension, even if in water or in alcohol or in other solvent, but it will be suspension. Okay. After that, you add this grit by this uh, uh, clips or something, and it will carry your sample on this grid. Okay. After that, you add it in the pink space. Of course, it is other. It is not simple like this. It's going inside the inside the instrument, and around it there are many lenses and many sophisticated parts. I'll show you what are the common microscope have. What are the common parts in microscope? The first one is electron source. This is the first. Second one is condenser of lenses. Both are condensed. Objective lenses. This is at object, which is the sample. And sample chamber. Of course, it has sample which you have holder. And detectors. These are common. But the difference is you will see the difference here. Only this is the difference between SIM and TIM. In SIM, the sample is by the end, and it reflects the beams to show, and you can detect the reflected beams. But in case of TIM, it transmitted some of the beam, and then you magnify these transmitted beams, and magnify again and again until you go to the scale you can see, and receive these beams to a detector, and you can see it and study it. This is TIM and SIM images. I'm sure you can see clearly that SIM image, it detects the substance or the material you add, is a sample you add from the top, like this. But in case of TIM, it sees in deep, it goes deep inside the sample, and you can detect. It's a very beautiful picture. That's why I present it here. It can detect the order and how are the atoms are arranged in on the surface. This is another example of same image, and this is other example of same image. Of course, you can see how the atoms are arranged and how much the picture is very beautiful. Now I think we go through TIM and SIM very quickly, and let's go to another technique if you don't mind. This is UV spectrophotometer. This is mostly common technique. In UV, it is before X-ray, as you can see. Its wavelength is longer than X-ray, but it is shorter than visible light. This is common one, as you can see. This is the sample holder, cuvette, which you put inside the instrument like this, but in the other part. This arrow should be on the left. This is spectrophotometer. I think most of you know it and used it. Okay, so in case of spectrophotometer, it measures the amount of ultraviolet and visible light that is absorbed, not adsorbed. There is a difference between absorption and adsorption. This is absorbed by the sample. Of course, the absorbed light depends on the material you are using and how much functional groups it has which can absorb this light. Okay, identify the quantity compound in variety of samples. Yes, it identifies the quantity means the concentration. Of course you have you can do it. There is kind of it's very simple experiment and a very simple technique. UV visible UV spectrum works by passing a beam of light through the sample and measuring the amount of light that's absorbed at each wavelength. Of course, the amount of light absorbed is proportional to the concentration of the absorbing compound in the sample. The more concentration means more absorption of the incidence light. Of course, it depends on a very old law, and it didn't change until now, which is Beer-Lambert law. A equals log I naught over I equals epsilon CL, where A, of course, is absorbance. Absorbance is dimensionless, and the I naught equals is the incident light, and the I is the transmitted light, whereas L is the path of the lens through the sample, which is almost 1 centimeter, and the C is the concentration. L, what is L? This is L. This is L, is the thickness of this sample. I think it is almost 1 centimeter or less. Epsilon is a constant known as the molar absorptivity or extinction coefficient. Let's go to this. How can we use this technique? It's very useful. I'll show you how much it's useful. UV spectroscopy is broadly classified into absorption, fluorescence, reflectance techniques, and something. Absorption, of course, it is fluorescence measures. It is absorption or reflectance spectroscopy. This is not our aim here. Instrumentation, it may be single beam or double beam. I want to go here. This is what will you use in UV spectrophotometer. What is it? You will go and make your experiment, take your sample, and add your the dyes. Of course, the dye will be colored like the left one. Okay, will be colored, and you check the light, and how much absorbance it will have. It will be very high. Okay, you go to your catalyst, add your catalyst, and make steering for some time, a time interval of 1 minute or 2 minutes or 3 minutes, whatever what you want. No, not what you want. I'm sorry. The controlling part is the reaction. If the reaction is very fast, you will have to take more samples at short interval times. But if the reaction is very slow, so you will have to take samples at much longer time. After starting the reaction, the concentration will be will decrease, as you can see in the right hand side. The concentration of green will decrease like this. This is concentration with time. And here on the left side, the concentration will decrease, means the intensity of absorbance A will decrease like this. And by time, it will decrease and decrease and decrease until it is very low like this. And this picture on the right side, it shows that the water is much clearer than the left side. Okay. If the concentration is high, then this absorption peak will be high. If the concentration is low, then the absorption peak will be low. And of course, whenever you add some, when you use some dyes, each dye will have its own lambda max, which you measure, and of course you trace the activity of the catalyst in this by this technique. This is, I will show you something else. This is one experiment which it's very famous, that for para-nitrophenol, it changes to, converted to para-aminophenol. Of course, this is this one paper, one published article, mine. It is mine. At here, you can see on the right side, it is no, it's on the left side, the difference between para-nitrophenol and the para-aminophenol. This peak is maybe 300 something, and the para-nitrophenol, the peak is 300, maybe 390. And this is the decrease of concentration by time. It goes like this. And this is when we plotted the linear form of first order kinetics with time like this. And this experiment is very famous, which is the reduction of para-nitrophenol to para-aminophenol. And the left one is very harmful one, and the right one is very useful in pharmaceutical industry. By this way, we traced, or we followed the reaction by measuring the absorption of para-aminophenol, para-nitrophenol, and para-aminophenol like this. One of the most important parts of using UV is the reflectance spectroscopy, in reflectance, where you can determine the band gap of the material. Sometimes you need to determine the band gap when you use titania compound, titania composites, or titania added something. You need to use determine the band gap, and by this there is an equation you can use band gap, and new instruments also, some softwares can determine it. I think one of the other most important techniques is the infrared spectroscopy. Infrared is very important. It's second one or same level of XRD. Even it is more famous or more common than XRD. And this is infrared just before visible, as you can see here. The wavelength is shorter or longer than visible light. In infrared, of course, it can determine the catalyst structure. And after you make absorption, after making absorption, you can detect what is the structure of the catalyst, or what the surface of the catalyst has. Like if it has basic sites, acid sites, at this time you can detect or make absorption of pyridine. if you add pyridine to the surface after cleaning the surface by evacuation and heating, you add pyridine. Pyridine will be absorbed to basic sites and acid sites. It will give different peaks. Like if you add CO, for example, it will give it will give you an idea if the catalyst is distributed or there are some agglomeration which is centering of the catalyst on the surface and NO and something. By infrared also you can trace, you can follow a reaction as well by in situ techniques. We will discuss it later on, inshallah. The most important, it has different types like absorption, transmission, and reflection. Of course, this is IR. Of course, these are the advantages of using IR. It is non-destructive. It is non-invasive. It can be adapted in measuring in the reaction conditions like in situ. It can be used at high temperature or very low temperature, no problem. This IR studies done under real process conditions, yes. And the last is you can use reactive probe molecules to quantify qualify and quantify the type of number of active sites. This is a chart of IR, and for this chart, I can tell you again, you will not invent the science. You will go to some tables like this. It has where is the functional groups can be detected in this scale. Okay. For IR, it can, if you make absorption for example, on CO, if you get a line or a peak from 2000 to this range, this means that you have linear CO on metal like platinum or copper or something. Of course, there is a difference, slight difference between each metal and the other one. And if you have rigid, rigid means CO is absorbed to two metal like this, triple bridged, three metal atoms like this. This means that you have condensed or not distributed. Your catalyst is not distributed well on the surface. And if you have geminal like this, geminal means two CO are connected to metal, or three CO are connected to metal, tricarbonyl. All of these, if you have special or detect peaks at specific places or specific wavelengths, this means that you have something on. You can see what exactly are there on the surface. And this is an example of using linear. This is real experiment on the left from this reference. And finally, thank you very much for your attention. Thank you.
So any questions? जैसे सर हम आईआर में फंक्शनल ग्रुप की स्ट्रेचिंग से पता लगा लेते हैं कि इसमें कौन सा स्ट्रक्चर फंक्शनल ग्रुप है। तो यूवी तो सिर्फ ट्रांजिशन बेस्ड होता है, यूवी स्पेक्ट्रम होता है। क्या हम इस वो किसी भी कंपाउंड की फंक्शनल ग्रुप या फिर उसके स्ट्रक्चर में जो फंक्शनल ग्रुप वो पता लगा सकते हैं बाय यूवी?
So he is asking any for the characterization of any molecule, for UV can detect the functional group of the molecule.
Yes.
Like IR can analyze the molecule having the functional group. Like
UV detects the electron transition. Yes. Each technique has its space which works for, but it can detect transitions like carboxyl or something. It has some peaks detected, or if you have these peaks, this means you have this If you know that you have, for example, if you have benzoic acid and you make UV, okay, and you detect a peak, this peak will be belongs to the effect of UV with functional group, which is transition, which is carboxyl. Okay. Of course, there is no table which shows that carboxyl will be detected at this functional group at this wave number, and some carbonyl will be detected here, and something like this. Of course, I think it's. Thank you. Sorry again.
Which technique is used most commonly nowadays, and what advantage does that method?
The most common is what you have.
Okay, in next lecture we will discuss, sir. Your problem will be solved by sir.
No, no. Do you allow me 10 seconds, okay? 10 seconds, I'll tell you. The problem is the most common, if I can arrange it, this is most common. For example, if you are working in organic chemistry, the most common will be just to check melting point, okay? Because each lab will have melting point. If each lab will have IR, so the most common will be IR. And the cheapest is the most common. The most available is the most common, okay? But you can arrange what you go to by expenses step by step. You can to go, for example, for TIM, which is very expensive, rare instrument, and leave XRD, which will tell you if uh, your if your material is correct or not. Okay, you can to go to sophisticated techniques and leave available techniques or common techniques. Okay, that's it. Okay, thank you. Okay, please.
Can we compare ethylene and tetrafluoroethylene whenever binds to metal?
Yes,
Using
ethylene. Ethylene.
ethylene and tetrafluoroethylene.
Actually, frankly, for myself, I work in pollution. Means try to make get rid of CO, NO, SO2 from air. Okay, and some dyes from water. Okay, but I didn't try to check ethylene or other compounds on by, for example, by IR. Okay. Yes, I didn't try it. Frankly, I didn't read about it, so I can't answer it. Just if I expect just talk anything, it will be useless. Just I didn't read about it, and I didn't do it by myself. But I have done a lot of work about absorption of CO and NO and SOxes and NOxes, and make reaction in situ reactions. Inshallah ta'ala, in next lecture or later on, I'll show you a lecture about this work, which can we do and what kind of results we can get, and how to interpret this result, inshallah, about what I did already. Okay. Okay. Any other question? Thank you very much. Thank you.
Okay. So thanks, Professor Zain Muhammad Ahmed Al-Bahi, and he delivered a very informative and very learning purpose lecture. Okay, thank you, sir. Thank you very much. So now the time of tea break, and then after tea, then we are again assemble at 11:30, most probably, or 11:15. So for the second lecture. Okay, thank you very much.